Hey guys, welcome to this video. Today I want to show you one of the examples of how to prove different things using induction, mathematical induction. Okay, so the task is, we need to prove that any n factorial, where n is greater than or equal to 3, you can represent that as a summation of n numbers, and each one of those numbers will be a divisor of n factorial. Okay, and those numbers will be different. So again, n factorial is equal to d1, d plus d2 plus d3, and so on up until dn, because there are n numbers. Each one of them are different, and also each one of them is a divisor of n factorial. Okay, so I can divide n factorial by any one of them, and the remainder will be equal to 0. Awesome, cool. So proof by induction. Okay, so the first step is the base. Okay. So for n equal to 3, what do we know? N factorial is equal to 3 times 2 times 1, which is 6, okay? And 6, how can we represent 6? That's basically, what? 3 plus 2 plus 1, okay? So we represent n factorial as 3 plus 2 plus 1. They're all divisors of 6, which is n factorial, okay? So it works perfectly fine for n being equal to 3. Secondly, so induction hypothesis. Induction hypothesis is basically this, right? For any n greater than 3, okay, let's say k, right? Oh yeah, let's do n. It will be possible to represent it as d1 plus d2 n factorial plus up until dn. And now inductive step. So let's try to do that. Okay, so what do we know? N plus 1 factorial needs to be also represented as d1, d2, d blah, 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 dn, right? Which will be divisors not of n, but n plus 1 factorial. Not n factorial, but n plus 1 factorial, right? So let's say, again, d1 plus d2 plus and so on, plus dn. Okay? Now, so the question is how to prove that. How to prove that if this is true, then this is also true. Okay, so let's see. So n plus 1 times n, okay, n factorial. And we already know what n factorial is, right? So basically it's n plus 1 times this, d1 plus d2 plus dn. Okay, and now here's what we can do. If we unwrap the brackets, right? So if we multiply n plus 1 by d1, n plus 1 by d2, n plus 1 by dn, then all of them are going to be divisors of this number, of n plus 1 factorial. So check this out. So n plus 1 times dn plus n plus 2, n plus 1 also, times d2, and plus n plus 1 times dn, okay? So each one of them, it's obvious that each one of them is a divisor of this number. So here's why. Because if I take this number, right, n plus 1 is definitely can be divided n plus 1, right? So those are the same, they're definitely dividers. And d1, d2, dn, all of those d's are also divided n factorial because of this, right? Because of what we because of the hypothesis we made in step number 2. So that's why that definitely works very well. However, there is a problem. So who can notice that problem? The problem is that how many numbers do we have here? We have n. And how many numbers do we need to have? We need to have n plus 1. Right? So that works like really, I mean, it may look like very easy to do, and it's like super simple to prove. However, like we run into this issue that we need to have n plus 1 numbers, n plus 1 divisors, but we only have n. So the question is what to do. Can you guys guess? I would highly recommend pausing this video right now and just trying to guess it yourself. But here's what you need to think. Here's what you need to come up with. Okay, so let's take a look at all of those numbers. we definitely know that n plus 1 is bigger than 1, right? So n plus 1 is bigger than n, and then multiply it by some kind of d. So each one of those divisors is going to be bigger than 1, right? And we also know that 1 is always a divisor, okay? So for example, if I have n factorial, right, I can always divide it by 1, and that's always going to be a divisor. The issue, so among those numbers, we definitely, so far, we don't have 1, but it can be there. We don't have a divisor which will be equal to 1, because this is already bigger than 1, right? And even if some of those d's is 1, the multiplication, the product of those is greater than 1, right? So there's not 1 anymore. So what you can think of is, what if we add 1 here, right? Like this. In this case, yes, we'll definitely have n plus 1 divisors. All of them will be divisors, but the summation of them will not be equal to this anymore. It will be equal to 1 plus n plus 1 factorial. So that's not legit. And the trick here is this. What if somewhere here inside we can basically unwrap one of those parentheses such that there will be 1? Okay, so here's what happens. Among those d's, somewhere we definitely need to have 1. Okay, so some kind of di, where I is equal to something, right? That's going to be equal to 1. In that case, we have n plus 1 times 1, which is equal to what? N plus 1. Okay, so basically instead of 1 divisor, now we have 2 divisors, right? So we add 1 more, which was missing, and that's perfectly, it's exactly what we're looking for. And now let's take a look at this number. So n, is n is a divisor for this number? Yes, of course, because like here we have n factorial, definitely. And 1 is also a divisor for that number, and we don't change the sum. Now the question you may have is, but how do we know that one of those d's is 1, right? How do we know that? Can we be sure about that? And unfortunately, the answer is no, we cannot be. So technically, it's not really obvious. Well, this is as far as I know. But what we can do, we can basically change the entire theorem, change the problem we're trying to prove, right? So we can basically create a different verbiage. We can paraphrase the problem which we're trying to solve. So we can say that we need to prove that n factorial can be represented as this, such that one of those d's will be equal to 1. Okay, so we're making this problem stronger. We're making it more restrictive. Okay, we're making it stricter, which means that if we prove that the stricter theorem is true, that means that the one which is more abstract is also true as well. I hope it makes sense, right? So if we prove that n factorial can be represented as a summation of divisors such that one of them is equal to 1, then it automatically proves that n factorial can be represented as a summation of some divisors. Okay, so it's kind of we're relaxing one of the restrictions, one of the conditions. Yeah, and in this case, like since we have base case and here we have 1 here, right? So that's kind of the hint here that one of those numbers is equal to 1. In this case, kind of this proof is automatically correct. I hope it makes sense. Hope you guys had fun. I'll see you guys later. Bye bye.